All right, Winter 22 P42. So recently there is a syllabus change in 2022, and transformers is not explicitly stated in the syllabus anymore, but in the syllabus they also didn't say they remove transformer. So if you're watching this video and you're wondering is transformer here or not, that's not important. The important thing is we know how to do the question. Okay, so let's try the question. So in this one, you are first asked to state Lenz law of electromagnetic induction. Oftentimes in paper 4, whenever they ask you to state a law, is because the next part of the question you have to use the law. Okay, so Lenz law talks about the direction of the induced EMF. And sidebar, Faraday talks about the magnitude of induced EMF. Okay, so I want to state Lenz law of electromagnetic induction. I would say that the direction of the induced EMF is such as to produce effects. Remember, this is the stubborn law. You want to fight the change. Effects to oppose the change in flux that caused it in the first place. Okay, so for example, the reason why I exist is because God decided I should exist. So I'm going to rebel against God because he caused me to exist. Okay, it's just human nature, you know. Okay, so the direction of induced EMF, you mentioned the term direction. That is induced EMF. This one is M1. So we need to set yourself up right first. Lenz law, always something to do with direction. And then the second one, you need to explain to me how to see the direction. Well, we will see the direction because the direction produces effect to oppose the change causing it. A1. So if the change causes it to go up, the effect has to go down. We look at the question now, okay? So try enough question so that you understand this law deep inside your heart. Okay, B. Here we have two coils, coil 1 and coil 2. This is a transformer. Transformer consists of two coils. One side, there is an AC current. But they also didn't call it a transformer. You know what, you guys? It doesn't matter. Read the question some more. It says that the current in coil 1 changes with time t as shown. So the current will go up, come down, go up, come down. Okay, it looks like a pretty standard alternating current. I can find the period, I can find the maximum current if I want to. Let's see what the question wants from me. Okay, the variation of T and I1 can be represented by the equation I1 is equal to X sin YT, where X and Y are constant. Use figure 8.2 or use the graph to determine the values of X and Y and give units to your answer. Okay, so I don't want to move my screen left and right, so I'm going to do a quick sketch of the graph law. Like that. The peak value is, you check for me, you check with me, 0.5, 0.6, 0.7, 0.75, 7, 8, no, 0.85. 0.85 I1 ampere. So obviously this one will be negative 0.85. And this one, 0.04, 0.08. Okay, so this one, X, if I write to the general form of the alternating current, is I0 sin omega t. So X is equal to I0. This will be 0.85 ampere. 0.85 ampere. Okay, what about Y? Y is equal to omega. This means I need to know the general form. Yes, this one you need to know. because you should be able to deduce what is the general form of most physical scenarios, especially in your A2. Okay, but if you struggle down, don't worry, I got you. Look at the formula sheet. You scroll, you see alternating current / voltage. X is x0 sine omega t. Let me borrow this. This means, right, X can be current, X can also be voltage. So if you generally have a problem remembering stuff, use the formula sheet. But please learn how to modify. Don't just blur, go and take only. Just go and take. It's just a bit sad if you do so. For formula sheet. Or formula page. Okay, regardless, y is omega 2 pi over t 2 pi over 0.04. Let me double check the axis of my x-axis. This one is in second. Wow, good. Good thing is in second, not millisecond. If not, it will cause quite a significant number of students their marks. Always check the axis. 157. Okay, so here's a question from anywhere. Teacher, 2SF, 3SF, how many SF? Well, most of the time I look at the question. You look at the numbers that they give you. You see this 4.6. This is 2SF. Correct? If you don't want to look at this one, I guess I can come back here. If you look at the smallest possible reading you can read, one box. Now one box here is 0.05. So like for example, this is 1.00. So all of this you can read to 2 decimal point, okay? Or some of it, let's say for example, if I take this one, this is 0.95, right? One box underneath is 0.95. This is also 2SF. Okay, so all of the values that you can possibly get, all of the data you can possibly get in this question is 2SF. This means your final answer should be 2SF, no? Teacher, what if I write 3SF? If you write 3SF, it's okay. No one gets hurt, it's fine. Just don't write 1SF. Okay, so this one should be 2 or 3SF. 2 is more standard. You write 3 also, never mind. Okay, don't worry too much about it as long as you show you're working. Okay, so generally speaking, this one, follow the significant figure of the data in the question. Okay, you're scared you forget, you write big and stick on the wall lah. Okay, so whenever you are confused, why suddenly there are 3SF one? Probably in that question they gave all the values in 3SF. Okay, what's the unit for omega? Unit for omega here, omega, right? That will be radian per second. Okay, because it's still angular velocity. All right. The current in coil 1 gives rise to a magnetic field in the iron bar. Assume that the flux density of this magnetic field is proportional to I1. So B is proportional to I1. Flux density proportional to I1. An alternating EMF is induced across coil 2. Transformer. The PD across coil 2 is measured using the voltmeter and has a r.m.s value of 4.6 volt. V.r.m.s. On figure 8.3, sketch a line to show the variation with T of V2 between 0 and 0.08 second. Okay, so I guess the first thing I need to do is to find my peak voltage. Okay, peak, I also call it V0 lah, alright? So V.r.m.s is V0 divided by root 2. So to find peak voltage, I will take root 2 times 4.6. This is 6.51. I just put 6.5 lah because 2SF. So this means this is 6.5. It is 5. 6.5 is here. Negative 6.5 is here. Okay. Graph paper print out a bit scuffed, but you get the idea. So now we need to draw the sinusoidal curve. Okay. And right now, we have to figure out where to put the curve. Should I draw a sine curve or should I draw a cosine curve? Okay, so a quick way to think about it is we want to oppose the change. So let me steal the graph. To steal the graph. Okay, so let me adjust the screen a bit. Okay, so I want to oppose the change, and the change is all from this current. So for example, when this current increase, right, I don't like this change one, so I want to oppose the change in that current. So now is a good time to actually pause and think about how would that opposition look like. But if you're good in calculus, you can actually borrow Faraday's law and differentiate how would that shape look like. Okay, so when this current increase in the positive direction, I had to have an induced EMF in the negative direction. So I'm going to start with the negative value first. Okay, and at this point, the current sort of like is constant for a short time. I1 constant for a short time. This means B constant for a short time. This means the induced EMF is 0 for a short time. 0 here. Is it 0? No, wait, 0.01. 1, 2, 3, 4, 5. 0 here. Okay. And then after that, you can see here the change is the greatest, 0.02. So the current should be the greatest, or the EMF should be the greatest. But also at the same time, because it is actually swapping in the negative direction. You see this? This is in the negative direction. So this current should also be in the positive direction. So I think from here, you can already tell current here is constant. So this one will drop back to 0. And then 0.04 will drop back to the maximum, the steepest point. So the steepest point will be here. So in other words, right, the graph that I'm drawing will look like negative cos. So this description is useful for you because Cambridge wants physics to be accessible. So we are going to assume people don't know calculus lah. But later I will sidebar and do the calculus version of answering this question. Okay, so this one will cut 0.07. Sorry, a bit ugly. No time to fix it. There we go. Okay, McDonald's sign. Can? So this is 3 marks because we need to make sure that the period is 0.04. The maximum value is 6.5 volt. So these two correct is already 2 marks out of 3. If let's say you get the phase relationship a bit wrong, that's okay, no problem. Don't be too stressed about it. Okay, so the other B1 mark is you either draw a cos graph or a negative cos graph. So you either draw like that, or I guess you can draw a W. Cos will look like this. Doing negative cos will look like this. Doing. Okay. Teacher, what is the calculus way? Well, you know my good friend Faraday, induced EMF is d flux dt. But this is also proportional to dB dt because flux is equal to NBA, and all the constant I don't have to care about it because the only thing I care about is the shape. If you feel happy, you put the constant outside law. So this is NA dB dt. Number of turn is constant, the area of the coil is constant. But also at the same time, you know, B is proportional to current. So maybe B is equal to Ki. I don't know what K is, and you know what? I don't really care. So this will be NAK, NAK, di dt. And what is I? Sine theta, right? D sine omega t dt. What happens when you differentiate sine? What do you get? Cos. Ta-da! Negative cos, to be specific. Because they don't really care about the direction, or rather direction is relative, at least for now. You draw either one is okay. Up to you. Some people want to show the opposition, immediately they put a negative, 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 negative. That's how they got negative cos. Okay? I mean, I can continue this, but this is trivial. It's not that important. The important is to know the shape. All right? And then plug in the values that you can deduce from the graph. All right? So the hardcore calculation is not needed here. Okay, last part. Use the laws of electromagnetic induction to explain the shape. I sort of started it a little bit already, but now I'm going to explain it for you. Number one, I will state the Faraday's law first. I will say from Faraday, because laws of electromagnetic induction starts from Faraday, right? So from Faraday's law, induced EMF which is V2, which is the graph that we draw just now, is directly proportional to the rate of change of magnetic flux. I state the law first because that was the law I used to deduce the shape. Okay? And then the second one, V2 is maximum when the I1 against T curve or graph is the steepest. Okay, so that would be this side here, 0.02. I highlight this side here, this side here. This so whoops, sorry about the jump. So this is the two places where the graph is the steepest, which means this one is maximum, this one is maximum. Okay, so V2 is maximum when the IT curve is the steepest. And then I explain the other point also. V2 equal to 0 volt when the I1T curve has 0 gradient. So when it comes to these terms like gradient, steepest, 0 gradient, this one has to do with rate of change of magnetic flux. Okay, because rate of change d dt has to do with gradient. And finally, this is already enough for 3 marks, but I'm going to write something else. I'm going to talk a little bit about the sign. Okay, V2 changes sign from positive to negative or negative to positive when the gradient of I1T changes sign. So what you really need to understand is whenever you see rates, it has something to do with gradient. Okay, so we are looking at how quickly the current is changing. If the current change very fast, then the value of V2 will be very large. So it would be helpful, I guess, before I end this question discussion, to just quickly sketch out for you how that looks like for at least one cycle. So for this one cycle, you can see there are parts where the change is very steep. So this part change very fast, this part very steep, change very fast, this part change very fast. So this value is maximum. Maybe I'll start with negative. This value is maximum. This value is maximum. This value is maximum. Okay, maximum magnitude. And then this part, so I'm going to label the point. This is point number, I guess, point A. V2 is maximum when curve is the steepest. So this one is point A. Okay. Point B, V2 is 0 when the curve is flat for a while here. 0 gradient. So this one is point B. So then V2 is 0 here, 0 here. Okay, more. And then V2 will change sign when the gradient change sign. Okay, so let's check out the gradient. Okay, steepness. You realize that here to here is positive gradient. Then here to here is negative value. Okay, so if I'm going to section out this part here, this one would be positive gradient. Then this one here would be negative value. And then it switch ma, saw or not? This part here switch negative gradient, which means here to here would be positive value. Now see, positive value. Okay, and then switch back again, no? So the shade here is V2 will change sign when the gradient of IT changes. All right, so hopefully that makes sense. So this kind of question is really testing your understanding and application of Faraday and Lenz law. Need more practice. Go and try all the questions that's already there.